Hi, everyone. My name is Julian, and for my EE431 project, I went a more analog route and designed a second-order switched capacitor Butterworth low-pass filter. First, I'll explain the Butterworth filter. Some of you may be familiar because it's a very popular form of a transfer function. The gain is set by resistors RF and R3. And the damping ratio is given by this equation here. The damping ratio affects the shape of the pass band of the filter and the existence of a peak at the cutoff frequency. The plot of the characteristic Butterworth response is shown here for different order filters. And notice the flat pass band and steep roll-off. For my design, I went for a second order, which corresponds to a roll-off of negative 40 dB per decade. Now I'll explain a little bit about switched capacitors. A switched capacitor is a technique of modeling resistance by controlling the charge on a capacitor. It works by using two switches connected to two clocks, phi1 and phi2, which are 180 degrees out of phase, as seen in this figure. In my project, the switches are NMOS devices. So when the clock is high, the device is conducting, and it allows the signal to pass through either to the capacitor or to the output. In the figure, there's no load, so the capacitor only is charging up and doesn't discharge when phi2 is high. And the value for the equivalent resistance is given here as a function of the clock frequency and the capacitance, and this will be derived later. So now that we know what Butterworth and switched capacitors are, I can write out a problem statement. For my filter, I want to design second order Butterworth with a 100 Hertz cutoff or minus 3 dB frequency called FC here. And I definitely wanted the characteristic negative 40 dB per decade roll off for a second order low pass filter. And I wanted the characteristic flat response in the pass band. And I also put arbitrary restraints on the switch capacitors and the area of the capacitors. So now to derive the parameters for the Butterworth filter, first revisit the transfer function, and knowing that the desired cutoff frequency is 100 Hertz, by setting the capacitors equal to each other at 1 picofarad, the value for the resistance can be determined. And as you can see, for a very low cutoff frequency of 100 Hertz and a very low capacitance, the resistance is required to be very big at 1.59 gigaohms, which would be pretty unfeasible using traditional resistors due to just the sheer area that a 1.59 gigaohm resistor would take up. But this is the advantage of using switch capacitor circuit, which allows a large resistance to be modeled. Then for the characteristic flat passband of a Butterworth filter, the damping ratio must be set to 0.707 or 1 over rad2. And this gives the ratio of the feedback and R3 resistors. Again, setting the damping ratio to 1 over rad2 yields the canonical approximate transfer function of the Butterworth filter. And from this, we can see what we expect the output to be for different inputs. So at F equals FC, we can expect the output to be, the filter response to be 1 dB. And so that's at the cutoff frequency. And in the passband, the filter response is expected to be about 4 dB. Now that the required resistance has been calculated in the Butterworth derivation at 1.59 gigaohms, the switch capacitors can be designed to model R1 and R2 here. So to explain more a bit about the switch capacitor, when Phi1 is high and Phi2 is low, the charge on the capacitor is equal to Vn times the capacitance. And for the opposite scenario, the charge is equal to V out times capacitance. So the change in the charge is equal to the change in the voltage times the capacitance. And then using the formula for the current through a capacitor, the equivalent resistance can be defined in terms of the clock frequency and the capacitor capacitance. For this project, I chose a switching capacitance of 50 femtofarads, and this is chosen, one, to keep the area down, and also to maintain a high clock frequency, which is important because in a switch capacitor layout, the clock frequency needs to be orders of magnitude higher than the input frequency. And the input frequency here is 100 hertz, and so the clock frequency is about 120 times this frequency, which is high enough. Now the circuit can be built and simulated in cadence using the switch capacitors in lieu of the R1 and R2 resistors. The reason it's not used for RF and R3 will be apparent later. So this first implementation uses the diff amp from the ADHL lib in lieu of the op amp seen in the previous schematics. Here the diff amp gain is set to 1.586, which was found in the derivation. And here's the response of the filter using the diff amp. You can see the pass band is relatively flat and the roll off is nearly 40 dB per decade at about negative 37 dB per decade. But the cutoff frequency is quite off at 22.1 hertz. So in order to try to model why this cutoff frequency was so much lower than expected, I attempted to take into account the parasitic capacitance of the NMOS devices. And looking at the layout lecture slides, analog transistors, which in this case they're being used in an analog implementation with a large W/L ratio, which these transistors have, tend to be affected most by the source to body capacitance, CSB, which here is modeled as a capacitance from the source of each device to ground in parallel with the existing capacitances. Here I ignored the capacitor associated with this NMOS device just for simplicity, because it is not as easy to model a capacitor with this node. However, this yielded a negative CSB value, so I knew that wasn't correct. So I tried to model them in series as well, coming up with a positive CSB value, which I then used to try to correct the switching capacitance value. Unfortunately, this had the opposite effect of what I wanted it to do. Instead of raising the cutoff frequency from 22 to 100 hertz, it further lowered it. So this means that my parasitic capacitor model was incorrect. And instead of modeling it further, I used the tweaking method to correct the switching capacitance in order to get the desired cutoff frequency. And after tweaking the switching capacitance to a value of 30 femtofarads, which was lower than the initial 50 femtofarads they were set to, I was able to get a better response with a almost exactly 40 dB per decade roll-off and a approximate 3 dB cutoff frequency of 100 hertz. and a relatively flat passband. Next, I implemented it with the rail-to-rail op-amp built by another group this quarter, in the hopes of getting the design into layout. And here I once again included the RF and R3 resistors and set them to have a gain of 1.56 as found in the derivation. And here is the simulation of the rail-to-rail op-amp. Sorry, right here is a typo, that should say rail-to-rail op-amp. And it shows a less ideal response, but still characteristically flat in the passband, and almost negative 40 dB per decade roll-off, and a little bit of error in the cutoff frequency, but it's fairly close. So then I decided to move on to layout, and here you can see the layout of the schematic using P-cells. The long skinny devices are the NMOS transistors, and the large square devices are the capacitors. And here's the layout with the I/O pads, showing 6 inputs and outputs corresponding to the VDD and ground signals, the input and the output signal, and then the 2 clock signals. And in conclusion, I was able to build a switch capacitor second order Butterworth LPF with an approximately 100 Hertz cutoff after tweaking the value of the switch capacitor. And the response was flat in the passband and had a roll-off of approximately 40 dB per decade, which hits all the specifications of the filter. Then my attempt to model the parasitic capacitance of the NMOS devices ended up being unreliable, but it's definitely an interesting topic to explore in future work, to model more parasitic capacitance and modify the transfer function to try to figure out analytically why the cutoff frequency was incorrect at first. And then finally, other future work would be to simulate the layout and possibly increase the order of the filter to see if a maybe negative 60 dB per decade roll-off could be achieved, and so on. Thanks very much for listening.